Hi everyone, welcome back to the course on understanding retrieval-augmented generation. This is the last lecture and we are finally going to be talking about RAG. We needed to wait until now because we needed to put together all the pieces of the puzzle. And in fact, we still need one piece of the puzzle that is about doing information retrieval on the web. So the big question is, can we apply all the things that we learned until now directly and blindly to web search? The answer, sadly, is no, because of two reasons. First of all, the web is huge, and second of all, it's very dynamic. So all the tools that we learned until now were mostly based on a small and static pool of documents. On the web, we have a new set of problems, especially recall, how to really calculate recall on the web. So the truth is that many of the things that we learned in the past lecture that were based on recall, we cannot directly apply on the whole web. Of course, we can apply it on a subset of it. If we are doing RAG on a specific website or on a pool of websites, of course, we can do that. But when we're talking about a search engine, for example, we don't have the luxury of calculating recall. So in fact, all those a big tech company like Google, they do different kinds of tests. One popular test is the A/B testing, where they basically divert a small proportion of the traffic and then use some automatic measures like click-through or maybe how much sales they made on that small proportion of the traffic, and that's how basically they see whether it makes sense to change their system. So we said that we would be using F1 measure to do this. In the case of a large search engine, A/B testing is used. Another thing that we can try to calculate, since we maybe don't have the luxury to actually ask users whether they like this search engine or not, is to compare the sizes of two search engines. And this is an important quality of a search engine, right? Supposedly, we want a search engine to be able to cover as many URLs as possible. So one more quantitative metric that we can use is to sample random URL from search engine A, see if they are contained in search engine B, and vice versa, and then compare these two sizes. So supposedly the one with the bigger size is better. So we have the problem of keep checking on the documents. What used to be our static pool of documents, now it's a huge amount of documents that keep changing. So we have to use some web spiders or crawlers that keep going through these pages. How? By following the links within these pages, and then these are indexed and stored and processed the way that we learned. They can be represented as word embeddings, represented as in a vector space model, and so on, plus some ads to comply with the business model of the search engine. So crawling, I'm not going to spend too much time on it, but it's simply keep going through the links of the web pages that we know, and until we reach a certain frontier, and then the rest is the unseen web. So we can decide where to stop, but what's important when you do crawling is that you remove duplicates and you make sure that the contents are good and relevant to the kind of data and application that you're working with. This is especially important for RAG. As we'll see, we're not really dealing with the whole of the web, but maybe with some just snapshot of some parts, subsets of the web. And the truth is that we are not really able to access the whole of the web. When we do crawling and we follow web links, we are just accessing the tip of the iceberg. There is a lot of stuff on the web that we don't have access to simply because they are not searchable. They are not connected to anything else. And these goes from financial records to legal documents, private documents in general, but also things that stay on the dark web. So because of all this kind of far west, we need some kind of trust. Trust is very important on the web. We talked a bit about trust when we mentioned the static quality scores, if you remember. That's why we went from just calculating TF-IDF scores to net score. So how to define trust on the web? Of course, we can have something similar to quality scores, but it's still not easy for me to understand and filter out, for example, fake news or misinformation or other things that I don't want my search engine to index. So this is an important problem nowadays because there is too much content out there, and the problem is how to filter out the one that is bad. But so we mostly use anchor text to see where the hyperlink is going. So this is considered a good quality signal because then it indicates what the hyperlink is linking to much better than maybe just going to the home page of a particular entity, for example. Sometimes these big companies, they have a very artistic web page that doesn't even mention their name. And so even the home page is not a very good indication of what IBM stands for. But if you then look at the anchor text and the link associated to them, then it's more indicative of how to find a node in the web graph that is more authoritative, a node that has a lot of inlinks. And in the past, people have exploited these to create the so-called Google bombs. So you could just create a web page and put it on your server or even your blog post, and then create a lot of other pages that link to this. And then Google would be fooled into giving results that are not really what they were meant to be, like the idiot Google bomb for Donald Trump. But this is still a strategy that many search engines are still partly adopting. Of course, search engines don't really still work using PageRank, but in principle, it's a good idea that is still taking into account the authority of each web page based on the number of inlinks and the quality of those inlinks. So for example, if you look at this page C, it only has one inlink. So we don't really care about the outlinks because you can add as many outlinks to your web page, right? But when we talk about inlinks, we're talking about another page referring to our page. And in this case, supposedly the score of C should be low because I'm only getting one in link. But the thing is that it's coming from this very authoritative page that has a 38.4% probability to be visited. So we're still talking about the probability, not really a quality score. And this is defined by the fact that B has so many in links, so many other web pages, so many other nodes refer to it. So these, you can consider these nodes as web pages with anchor text that is linking to B. So because B has such a high score, then C inherits some of this score because B is actually only linking to C. If B was linking to other pages, this score would be lower. So it's kind of a quality score that we are measuring there, but at the same time is also a probability, like a random walk. If you just randomly go through this graph, what is the probability that you end up visiting this page? And in fact, this is exactly how we also need to be thinking about the web. So until now, we just talk about documents and the words that make up these documents and calculated probabilities based on this. But when you talk about the web, of course, you also need to take into account the graph structure of the web. So that's why we are talking about these probabilities, and PageRank does exactly that. So it calculates the probability of ending up in a certain page based on the probability that we get from other pages, but also taking into account the inlinks and outlinks. So for example, here the page rank of page C is the probability of ending up on page A divided by 2, because once you're in page A, you can go either in page B or C. So once I'm in page A, I have a 50% probability to go into page C, plus the probability of B divided by 1, because I only have one outlink that goes exactly into C. So this is what I was talking about earlier, random walk. In order to calculate the probability of me visiting a web page, I can assume that I have a random walk. So you can think of it as a crawler, one of those spiders that we talked about before, although the crawler is really just following links. And we're talking more about Markov chains and long-term visit rates. So if I keep repeating this random walk, and then I calculate an average of the likelihood or the probability for this random walker to be at this page, this is how I get PageRank. Again, this is not how Google works today, but it's still was one of the fundamental algorithms that were used in the early stages. So we're talking about Markov chains that just model the probability of going from one state to another. So here you see a very simple case of random walk that tells me what is the probability of going from a sunny day to a rainy one and vice versa. So here we see that if it's sunny, there is an 80% probability that it still stays sunny, but there's also 20% probability that it becomes rainy. Once it's rainy, I have a 40% probability that it stays rainy, and then 60% that it goes back to sunny. So this is helping me model different stages of a graph that is very applicable to the web graph. So let's say we have a situation like this. So these are web pages or our documents in the information retrieval sense. And then these are our hyperlinks with anchor text. So for example, on document D0, there is an anchor text card that links to document D2. And then on D2, we have anchor text GM that links back to D0. So all this graph is telling me how I go from one page to another. So this is important to understand, because on top of modeling these documents based on the words that make them up, like we have done calculating TF-IDF scores and vector space models and whatnot, now I also have to take into account this probability. So this can be our quality score that finally results in the net score as well, where I have both the relevance of the document, but also what is the probability of someone visiting this page. How can I build a matrix for this representation? So this is nothing new. We have done this many other times when we were talking about the inverted index, for example. I can just do as I used to do earlier. I represent all my documents or web pages, and then when there is no link between the two pages, I have 0. When there is a link, I have 1. So this, for example, tells me that D1 is linking to D2, but also to itself and to nothing else. So this is just a representation of this graph that we've just seen. So D1 was here as linking to D2 and also to itself. Then if I want to convert this into a probability, then I have to normalize it. So those two ones that I had here become 50% probability because I had 2. In this case, because I had 3, becomes 0.33 and so on. So this is all good, but still it doesn't really model well the way that a common user would visit the web, right? There is also the chance that someone would just close a tab and open a completely new web page, right? So in order to model this, we add this alpha or teleporting rate. So we add alpha divided by n to every entry to take into account that at any point we can also jump from a page to another. We don't have to always follow the links, right? So this helps us to calculate the long-term visit rate. There is just a problem that sometimes there are some dead ends. So if we don't have this teleporting rate, there is the risk that we get stuck into this dead end. So it's important to have this teleporting rate, not just to better model the user behavior on the web, but also to make sure that the Markov chain is ergodic. So at a leaf node or a dead end, I will have this teleporting probability that allows me to jump to any other part of the graph, and in other links, I will still have the probability that is given to me by the links plus this teleporting rate, because once again, at any page, I can either follow the link or jump to any other page. And this again is important because it makes the Markov chain ergodic, and we like to work with ergodic Markov chains because they are irreducible and aperiodic. So it basically it makes sure that we can reach any page from any other page, and there are no loops inside the graph, so that maybe I get stuck in the same subset of the graph. So teleporting, it's exactly useful for this. It makes the graph ergodic, and that's why PageRank works. Okay, so PageRank, very important historically because it modeled the first algorithms that were used by search engines, but it has a lot of issues. First of all, that teleporting rate that we just talked about is not really modeling well the user behavior on the web. People don't just randomly jump from a page to another. There is always some reasoning behind it, right? That's why later we'll talk about agents. And also PageRank can produce bad results for a lot of pages. So in practice, you use different models that look at, of course, the content of the web page, and also some way to calculate how important, again, a page is based on the quantity of in links that it has. So yeah, the frequent claim is that PageRank is the most important component of web ranking. In reality, is just a good idea that has evolved so much that now it's almost completely different from the original algorithm. So another idea that maybe can try to improve on PageRank is HITS, hyperlink induced topic search. And this is slightly smarter because it tries to individuate in an iterative manner hubs and authorities. What is a hub? Is a page that has a lot of outlinks to other pages. Authorities instead are the ones with a lot of in links. So we can have an algorithm that keeps iteratively counting how many in links and outlinks we have to define what are the top authorities and hubs in our subset of the web. And of course, it's very difficult to do it in one shot. It needs to be an iterative algorithm. We start with the root set, and then we start looking at, for example, the outlinks to find some hubs and the in links to find some authorities. So then I keep expanding and iteratively increase the score of the hubs, the H score and the A score, until it converges. So I have my list of top authorities and hubs. So this is quite easy and smart. The only problem is that it cannot be pre-computed. So with PageRank, we were pre-computing the long-term visit rate, the probability of a random walker to end up in that page. With HITS, we can't really do that. So that's one problem. But in any case, these are two of the possible ways that we can model authority on the web. Again, those kind of quality scores that we were calculating earlier. Okay, so we are nearing the end of the course. Let's summarize what we learned so far. So we've learned in the previous course, the course on NLU, we talk about data representation, and even in this course, in the lecture one, we talk about one-hot encoding, bag of words model, count vectors, and so on. Then we went on to talk about vector space model, how we represent data and documents in multi-dimensional vector spaces. So we talk about term document matrix, TF-IDF. In the NLU course, we also talk about dimensionality reduction. And then, of course, we talk about how to calculate similarity between these data points in the vector space, either by cosine similarity or by Euclidean distance. And then recently we talk about how to process queries. We talk about things like spell correction, but also query expansion, cluster pruning to optimize query processing, the pseudo-relevance feedback, and so on. Then, of course, we talk a lot about some pre-processing techniques, natural language processing techniques. This is more from the course on NLU, and when we were talking about those syntactics processing in the suitcase model. We talk about how to encode also semantics using word embeddings. This is also something from the NLU course. And finally, also large language models that are a bit more advanced and more able to encode pragmatics and tackle more complex NLP tasks. Then finally, in the past few slides, we talk about web search and web graph, how to model authority and trust on the web. So finally, it seems that we have all the pieces of the puzzle to talk about RAG. So what is RAG? RAG stands for Retrieval-Augmented Generation, and it basically puts together the power of information retrieval, what we learned in this course, plus the power of generative AI, which is something that we covered more on the NLU course. So we're going to see how all these pieces together make up RAG. So in theory, we already know what RAG is because we have already extensively talked about all these pieces of the puzzle. We just really need to understand how they come all together. So we're going to do that in a minute. We'll see the different phases of RAG, the phase that happens offline, or better, before we receive any query from users, and the online phase that happens in real time when I get a query and on the fly I need to find the relevant documents and provide an answer to the user. But before we do that, we need to clarify what RAG is not. So some people think that especially when you use ChatGPT and you see that ChatGPT is searching through some web pages, you think that ChatGPT is kind of doing a Google search, right? But actually, that's not what happens. RAG is not you asking a query to a large language model, the large language model doing an online search and then giving you the answer. This would be completely inefficient because it would take so much more time to give you an answer. It would raise questions of reliability and quality control because then you never have the luxury of knowing beforehand what kind of results you get from a search, and also it would be very expensive for a large language model to be able to access and process stuff in real time from the web, and many other issues that are listed here. So that's not what's happening. RAG doesn't entail making a real-time web search. In fact, the indexing is done beforehand, and we'll see how in a minute, but then you can see RAG as the three main components: the retrieval part, the augmentation, and then the generation. So basically it's creating a better large language model that instead of just giving you general answers about a query, it enriches it or enhances it with some more up-to-date information. So this up-to-date information is coming from either your own document database or vector database, which can be updated either daily or weekly or monthly, depending on the domain. So in a nutshell, you can see RAG as search first in a vector DB, then and enrich the query, expand the query with the information that we got by doing information retrieval, basically, and then using the large language model as a front end to give a more personalized and ad hoc answer. And this really addresses the key limitation of large language models, right? Because large language models are extremely powerful and able to answer to most questions about general knowledge, but then they are only as good as the training data that has been used to train them, right? And we don't have the luxury, as we discussed in the previous course, to keep retraining a large language model. So that's when RAG comes into play. And it's really to address mainly this limitation that we don't have the luxury to retrain a large language model daily or even weekly or even monthly. So instead of doing that, we access a vector database or a document database that can help me provide a more up-to-date answer. And many of you maybe forgot this, but last time tools like ChatGPT were really not very useful, because every time you ask a question that really requires more up-to-date information, the tool would just tell you, sorry, my knowledge cutoff is in September 2021 or whatever else, and I'm not able to answer your question. So now that's not happening anymore, thanks to RAG. So it's a huge step forward. So RAG allows me to have real-time updates, much more accurate, ad hoc information, and it's also much more scalable than large language models. So the big difference again is that I have a knowledge base that is no longer static, is dynamic, because I have this smaller portion that I can query with more up-to-date information. Supposedly is also more accurate because it's more grounded in real data. Basically, it's not just about having up-to-date information, but also providing more context. So the answers are not just more recent, but they are also more accurate and less prone to hallucination because I'm providing more context to the query. And also it can be very specific to your own personal preferences or whatever the application domain that you need the answer for. While if you use like a vanilla LLM without RAG, it would maybe give you a very general answer that is not that useful. So before we go into the implementation details, we also need to clarify when to call for RAG, right? So this is similar to the discussions that we had, for example, for spell correction or many other of those optimization techniques that we talk about. So it's not like RAG needs to be applied every single time. So I need to have a kind of router that tells me, okay, this query requires RAG and this doesn't. Again, similar to last time when we were doing spell correction for our information retrieval system, we don't do spell correction every time because it comes with the cost, mostly time cost. So I only do it, for example, when I don't have many results or I have 0 results. So with RAG is slightly more complicated, but still is a similar concept. I don't always use RAG. I use it when I know that the query requires me to access this more up-to-date vector database, when the query is about something that is time sensitive, when some external grounding is required, when the query is a bit ambiguous, or when it's a bit rare, like when the system realizes that it doesn't have enough training data to answer this question, then RAG is a good alternative, and also depend on the kind of wording that the user uses. So yeah, there's gonna be some strategy that is important, a sort of router that tells me once I receive the query whether to go and use RAG or just use the LLM directly, and this is an important strategy to have. Again, it depends on the question. If it's a general question, no need to call RAG. Otherwise, if the system realizes that it doesn't have enough training data to answer that question, for example, if it's able to calculate an hallucination score and this score is too high, then it's better to go for RAG. So I have to implement a sort of gating function that tells me when to use RAG. So we answered the what, we answered the why, we answered the when question. Now it's time to answer the how. How do we actually do RAG? So let's go back to that slide that we mentioned earlier with the two phases. I'm gonna go through each of these phases and sub tasks based again on the things that we learned already. So once again, the web search piece of the puzzle doesn't mean that we are going live and do a web search. It means that before I receive any query, I decided what kind of documents I need to crawl and index based on my application domain. Or I can just blindly take a corpus from Common Crawl or other resources that weekly, monthly, or even daily take a snapshot of the web. So again, I'm going to be applying some NLP techniques to clean this data. So once I have put together, let's say, all the web pages that are relevant to my application, to my domain, to my business, I want to make sure that these are clean of duplicates, of things that are not relevant. And these are all the techniques that we talk about during the NLU course: parsing, text chunking, and so on, to pre-process the data so that it can more easily be represented. How? In our usual vector space model. So maybe here these days we are not really using TF-IDF, but that's definitely a possibility, as we'll talk later. Maybe we'll be using also some word embeddings to represent these web pages in a multidimensional vector space. And last but not least, I do a bit of more of cleanup and understand, for example, what are the important clusters or categories that I have in this vector space model, so that whenever I receive a query, I can be faster at getting all the relevant documents and then providing an answer for the large language model. So this, you can think of this phase as, for example, query optimization phase, like cluster pruning. We haven't received the query yet. We're still at phase one. We're still offline, but if I can organize my vector space into clusters and, for example, assign a leader to each of these clusters, then later when we receive the query, we can apply cluster pruning or any other optimization techniques that we learned. So the first thing to do when I receive a query is to also represent it as a vector and put it into my vector space model. So once the query is there, then I can apply all the techniques that we talked about earlier, including calculating the similarity between the query and some of the documents. Here, of course, it will be important to do some query optimization, because if I have millions of documents, then I don't have the luxury to calculate the cosine similarity between the query and all of those. I will have, once again, to think of some strategy like cluster pruning, for example. So when I finally get the top K documents or web pages that are relevant to the query, I have to package them nicely and use them as context for the large language model. So I can use these vectors that have a high cosine similarity with the query, merge them together, feed them to the large language model that will finally provide a very contextualized and supposedly very relevant answer. Why? Because on top of using its general knowledge, it will use the context that I'm providing through my vector database. So it's a bit like we're doing automatic prompt engineering, right? Instead of manually writing the prompts, we use all the things that we learned in this course to retrieve the most relevant documents to the query and then use these documents as context. Okay, so that was RAG in a nutshell. And again, we have seen through the course of this course and the previous one what each of those pieces of the puzzle mean and how to implement them. But then, of course, there's more than meets the eye. If we want to build RAG from scratch, then we have to make some implementation decision for the indexing part, the retrieval part, and the generation part. So in the next few slides, I'm going to be talking about these just briefly. If you want to know more details, you can look at this link, centec.net/retrieval-augmented-generation.pdf, where you have all the information to specific resources that you can use to build your RAG system from scratch. So when it comes to indexing, we have several options. Sparse vector indexing is what we have seen in the first part of this course. TF-IDF, for example, can be considered sparse vector indexing because it builds a very simple yet effective vector space model, and it works if you don't have to represent too many documents, and also if your data is well behaved and it's also cost efficient. Dense vector indexing is slightly more sophisticated. It's using word embeddings and transformers to take into account the context better, but is computationally more expensive. And you can have also a mix of these two, as we said last time, for by word versus positional indexes, depending on the types of data that you're processing. You can apply one or the other strategy. For example, you can use sparse indexing to recall relevant documents from a very big database and then use dense embeddings to rank the recalled documents. Then we have data where we are dealing with graphs. In that case, we need something different, something similar to what we just talked in the first half of this lecture, PageRank or hits to take into account the authority of each node in the graph. So that does it for indexing. Now let's go to retrieval. We know very well what retrieval means and how to implement it. Sparse retrieval, once again, is TF-IDF, so computationally less expensive, but it's ultimately just bag of words and it's not as efficient as word embeddings, which is again dense retrieval. So this definitely more efficient, but also more computationally expensive. And then we have, again, graph-based retrieval for those kinds of data that need to be represented as graph. So it can be databases of people or name entity and the relationships between them. So we need to be able, on top of looking into what makes these documents, also use, again, PageRank or hits to model also their authority. Then we have self-adaptive retrieval, which is similar to what we just talked about earlier for indexing. It's kind of a hybrid system that decides what strategy to apply depending on the query, depending on the data that it's handling. Multimodal retrieval is per se a very important branch of research. these days, because the data that we work with is more and more multimodal. And so when you work with different modalities, there is a completely new set of problems, how to retrieve and also later on generate data that is relevant to the query. So different strategies can be applied here. The simplest would be to translate every modality into text by converting, for example, a sound or an image to a description of it. But this, of course, would come with some limitations. So that's in the best case scenario, we try to efficiently fuse all these different kinds of data and many more. For example, if you are dealing with long documents, then you may have to take a more fine-grained approach where you split up every document into different sectors or sections or paragraphs so that you are able to find a specific section. For example, if you need some legal advice in a very long document, then that's when you have to apply long document retrieval. Okay, so now the last bit to look at is generation. We haven't talked much about this in this course, but we talk about generative AI in the NLU course. Here, very simply, you can, again, apply different strategies depending on the resources available. So if you have limited resources, you can use a template-based generation. So let's say your goal is to use RAG to create a report or different kinds of report that always look like the same. You can just use a template and force the generator to just fill in the blanks, basically. The next step, when you don't have fixed templates, is to apply some rules. So in this case, you don't have fixed reports, fixed templates, but you can still create a relatively simple generator that is based on rules. Next, if we don't have the luxury of having some rules or template, we can, instead of using large language models that are very expensive, I can try to use those sequence-to-sequence models that we talked about in the NLU course. But ultimately, the best is to use a large language model if I have the means. And that's when you have RAG at its best, because it puts together, once again, the general knowledge of large language models and the domain-specific knowledge of RAG systems. So there's one last thing to talk about, which is Agentic RAG. What is Agentic RAG? We put together Agentic AI with RAG. So RAG, by now, we know what it is. And what is an AI agent is an AI algorithm that can act on its own. So instead of receiving single instructions or single prompts, it has a goal, and it has also the autonomy to do several actions to achieve this goal. So the difference between agentic AI and the AI that we talked about earlier is that, again, instead of just having a fixed input and one specific way to try to generate or produce an output, here we have a goal as an input and different possibilities to achieve this goal. And agentic AI is also useful when we don't have just a one-off task, but maybe a task that needs to be repeated. And RAG is a good application for this because we have to keep our vector database updated, right? The biggest difference, to go back to the comparison between large language model, RAG, and now AI agents, is that not only it's dynamic, but it can also perform actions, and it can break down complex problems that RAG by itself wouldn't be able to solve into smaller ones. This is similar to the concept of task decomposition that we talked about earlier. It has the autonomy to decide how to achieve these goals, so it can try different strategies by trial and error and decide which one is the best. And it's, again, best for those kind of more complex applications. So if I have a simple task, I can just apply vanilla RAG. I don't need to go for Agentic RAG. Agentic RAG is best when I have a complex system to maintain, to keep updated, but also the kind of queries, the kind of requests that I get from the user requires a certain degree of intelligence. And this is considered by many the future of RAG and web search in general, because then it creates much better results that can be, again, also be explainable. Because then if I have one agent or multiple agents that are carrying out several tasks, then it's easier for me to ask questions on how this output has been generated and why. So again, what is an agent is an AI algorithm that has the autonomy to make decision and act on its own to achieve a specific goal. So in this example here, I have access to a vector search engine, one of those vector databases that we were talking about earlier. I have a calculator. I can even access a web search in real time. Maybe I have access to my email and my code and whatever else is needed to carry out the task. RAG can be represented like this, as we've just explained in the earlier slides. We have these tasks: retrieval, augmentation, and generation. And these are all tasks that can be tackled by an agent. So in a single agent RAG architecture, we have this retrieval agents that basically can access different vector databases depending on the query that it receives, or a calculator, or even do an online real-time web search if the information that I need is not contained in any of the collections available, and then pre-package this information as context for the large language model that provides the final response. In a multi-agent architecture, we have something slightly more sophisticated. We have something like a super agent that is doing task decomposition and giving different tasks to different agents with different expertise, and then combine all the results from, for example, the vector search engine across different vector databases, some online web search if available, and maybe also an agent that is telling me about relevant documents in my email or in my code. And finally, fuse all the information together and feed it to the LLM that once again acts as a front end for the final response that will be very specific and very useful for the user. So you understand how an architecture like this is needed for applications that are more complex. I cannot think of using a vanilla RAG for problems that are very fine-grained and multifaceted. So, for example, applications like enterprise knowledge management, when I have to put together a lot of information coming from different parts of the organization, customer service, when some complex queries need to be handled, intelligent assistant that can do a lot of different things beyond just answering queries. Research and science, of course, when every research question is a very complex and multifaceted problem to address. Content and creative writing also can be useful to look at the different facets of creativity that eventually come together to create a work of art. Education and e-learning also, that's a place where Agentic RAG can help to personalize the experience that students have in the learning process. Healthcare and medical informatics as well, to have a more holistic vision of patients and all the different perspectives that we can have for patient care. And finally, also legal and compliance in terms of having different agents that can look at not only the usefulness of some legal advice, but also how to minimize risks. So finding the trade-off between two different quantities can be important. So these are just examples. There are many more applications where Agentic RAG can be key in the future. But there are also some risks. So the problem is, as we have more and more intelligent and personalized tools that can help us basically find the things that we need, or even do the things that need to be done, as we discuss in this work, there is the risk that we detach too much from other human beings. So there's always the problem of finding a trade-off between what AI or Agentic RAG can do for us versus the things that we should do ourselves. And because of this, some are already talking about the transition from an attention economy, which is what we have now, to a relationship economy. Because then if we push this to the limit, we will have that every company will have their Agentic RAG or their chatbot that is doing things for us, like buying things for us or giving us suggestion about the products of the company. But we need to make sure that this kind of relationship is transparent and not abused by these companies. And so there are many more things to discuss, and we are towards the end of the course, so this is not maybe the right place. But another important problem is so-called AI overload. So the fact that, for example, AI is enhancing our productivity so much, it can also be a cause of stress. It can be a double-edged sword, because then if AI can increase our productivity at individual, organizational, and societal level, then that maybe also means that more is expected from us. So in general, what's happening is a bit of a narcissistic wound for us, as Freud used to call them, and some compare this to other revolutions that strip humanity of some core human beliefs, like the Copernican revolution that stripped us from being at the center of the universe, Darwin that told us that we are not so different from apes, Freud who said that we are not really in control of our minds, and finally the AI revolution that for the first time it puts other intelligent beings in the universe. Now with AI, we are no longer the only intelligent beings on Earth and in the universe in general. So I don't want to end with the negative note. That's why I added this final slide. In general, as we discussed through this and the previous course, I am quite optimistic about the future of AI and humanity, how human and AI together can overcome their weaknesses. And the best case scenario, again, is when you have a human in the loop that is using AI to achieve things that he or she couldn't achieve on its own. And information retrieval and RAG is similar in that sense. Some people now are talking about grounded or embodied RAG, but I have no more time to discuss, so I'll leave that up to you. I hope that with all the things that you learned in this course, you are well equipped to go and build the future of information retrieval. And I hope that you enjoy this course. Thanks for your attention, and see you next time. Ciao.